Good morning, students. So, have you completed your homework problems? Have you all completed? So, what is the answer for first problem? So, three cases are given. So, you have to use timer 0 in three modes, that is 13-bit timer mode, 16-bit timer mode, and 8-bit auto reload to generate square wave of 2 kilohertz. So last class I have explained the calculation for 2 kilohertz. What is the initial value for 13-bit timer? Please tell me. So what is the initial value? 1F, 1F, 1A or 1F, 19? Please check, Balameenakshi. 8192 minus 250 microsecond divided by 1.085 microsecond. Please, students, please answer. 8192 minus 250 microsecond divided by 1.085 microsecond. So what is the answer? So your answer is 230. Okay. You subtract that 230 from 8192. Find out the value. 1F, 1A, I think so. So others can post your answer in the chat box. Have you completed or not? One F, one A. Okay. So that value is 16-bit value. 1F, 1A is a 16-bit value. So you have to convert that value into 13-bit. So how do you convert that? 1F, 1A is a 16-bit value. So your timer is going to run in 13-bit timer mode. So you convert that 1F, 1A into 16-bit value. So first you write it in binary and separate the bits into 5 bits and 8 bit and find out the answer. So to calculate your initial value, first you convert that frequency into time period. Okay, so the given frequency is 2 kilohertz. Your time period is equal to 0.5 millisecond. That is equal to 500 microsecond. Okay. So divide this into 2. Divide this time period into half, 250 microsecond for on time and off time. So consider either on or off. Okay. So the calculation for calculating, that is the calculation for to find out your initial value, 8192 minus 250 microsecond divided by 1.085 microsecond. After subtracting, you will be getting 7962 in decimal. Convert this into hexadecimal, 1F, 1A. Okay. So first you write it in binary because this mode is a 13-bit timer mode. So you have to convert this value into 13-bit. 1010. So separate the entire 16-bit value into 5-bit and 8-bit. So your lower LSB is 1A and your MSB is F8. 4X along with 100 F8. So this value is to be loaded into your timer higher order and lower order register. Okay. Please note down the calculation. Are you able to follow? Yes or no? Please respond, students. Can you understand this one, this calculation? You understand? Okay, please note down and convert the value for 16-bit. Find out the initial value for 16-bit timer. So please do it fast. Okay, we have to complete our portions. Okay. So what is the answer for 16-bit timer? Can anyone unmute and tell me the answer, please? Divya, please tell me the answer. Divya T. Divya, are you there? Indu, Divya,
ma'am.
Tell me the answer, ma. Homework problem, you have to complete. For 1 hour la vandu.
SS 1A.
What is the answer?
SS 1A.
அது ஏன் நீங்க chat boxல
FF 1A.
only few students are communicating with me. நீங்க remaining 65 என்ன பண்றீங்க? ஒரு faculty வந்து we are asking, we are teaching through online mode na, you have to communicate while teaching problems.
Okay, ma'am.
Okay. Very few students are frequently communicating. Remaining எல்லாம் வந்து அப்படியே silent modeல இருக்கீங்க. Okay. What is the answer? 16-bit FF1A. For 8-bit, for 8-bit mode, so subtract. So your decimal conversion is 230. Okay. That is 250 microsecond divided by 1.085 microsecond is, what is the answer? 250 microsecond divided by 1.085 microsecond. What is the answer, ma? 230, I think so. 230. So subtract this value from your maximum value. Find out the answer. The answer is 1A. Please check it out. Are you getting this value? One A. What about remaining students? So what is the logic involved? How to generate square wave? 2 kilohertz frequency wave using timer modes. What is the first step? Please tell me. What is the first step? Sweta. What is the step? First step, ma? Sweta. I cannot unmute, ma'am. Okay. Post your answers in the chat box. So first step would be you have to load your T mod value, okay? So move T mod, comma, hash 00 for 13-bit timer mode, okay? For 13-bit timer mode, your T mod value is 0. First, your T mod is loaded with 0, and next you have to load your initial value of timer. So here I am using timer 0, so TL0 and TH0. You have to use timer 0 lower order register and timer 0 higher order register. So here you have to load your initial value 1A and here F8. So after loading this value, you have to start your timer by using this instruction set bit run control bit. Start your timer. Okay. And next step, once your timer gets started, you have to monitor your overflow flag. Overflow flag continuously by using jump no bit instruction. When TF not is equal to 0 means the condition is true. That case, your program will execute the same instruction. It will continuously monitor the overflow flag status. Suppose your TF not is equal to 1 means the condition is false. That case, it will execute the next instruction. Okay. Here, you have to generate your square wave by complementing your port 1.5. Okay. After that, when overflow flag is set to 1, user responsibility is that we have to stop the timer and clear the overflow flag. Okay. So next, SJMP. So your L2 should come to which place? T mod or move L naught, move H naught. L2 should come to here in case of your 13-bit time. So your program control goes to L2. Your L2 is your loading your initial value. So this is the program for 13-bit timer. Suppose next in case of 16-bit timer, what are the changes to be made in this code? Please tell me. So what are the changes to be carried out when the timer is in 16-bit timer mode? Please tell me. See, I have explained 13-bit timer. Suppose your timer is in 16-bit timer mode. Call delay, okay. 0, 1, set bit, clear bit, call delay, okay. FF1A. Okay, correct, Balameenakshi. So my question is, so already I have explained this 13-bit timer. 16-bit timer na enna changes பண்ணுவீங்க same code la? Please tell me. T mod and TH TL values. Okay. So what is your T mod value for 16-bit timer? So your T mod value is 0, 1. Okay. So here move T mod comma hash 0, 1. Okay. What is the next step? Move TL not comma hash. So what value to be loaded into lower order register? So lower order register value 1A and higher order register value FF. Okay. And remaining instructions will be same for 16-bit timer. The same logic can be applied for 16-bit timer. The only changes you have to define your mode based on the mode selection and also the initial value of the timer based on your timer maximum value. Okay. So suppose in case of 8-bit auto reload, what are the changes to be carried out? In case of 8-bit auto reload. Here, in case of 8-bit, the position of L2 can vary. Very good, Rohit. Okay. So the here, in case of 8-bit auto reload, you have to load your initial value to TH naught, not TL naught. Your microcontroller will take care of loading your initial value from higher order to lower order. What is the difference? Any other difference comparing with your 8-bit auto reload with your 16-bit timer? Any other difference in your program? Position of L2, okay. Next one. T mod is 0 to, okay. The important thing is we need not load the value for reloading the value in order to repeat the operation. Okay. So here L2 comes here. That is set bit TR naught. That is the difference. And here TH naught, this statement is not necessary. So after the overflow flag is set to 1, your microcontroller automatically gives a copy of TH0 to TL1. The original value is automatically reloaded into the TL0. So this step is not necessary. So you have to initialize at the starting of the program and repeat the operation. Your microcontroller will take care of this reloading this value. Okay. So what is the second problem? Generate square wave with on time of 3 millisecond and off time of 10 millisecond and all the pins of port 0. No need of initializing again. No, okay. That is the difference of difference between your 16-bit timer and 8-bit auto reload. Okay. How do you calculate different that is time period, the initial value of timer for different time period? So the on time is 3 millisecond, off time is 10 millisecond. What is the logic for this particular application? Please tell me. So here you have to generate square wave with on time of 3 millisecond and off time of 10 millisecond on all the pins of port 0. Here you have to use timer 0 in 16-bit timer mode. Can anyone explain the logic of this program? Gopinath, can you explain that? Gopinath? Sabari? Sabari? Aditya? Aditya, are you there? Aditya? Akshaya? Akshaya? Akshaya is here? Yes, okay. You can explain. So what is the logic? See, you have to generate square wave with on time 3 millisecond and off time 10 millisecond. So what is the logic? Ma'am, exactly I don't know. So what is the reason? Hmm? You can tell your views. Even if it is wrong, you can tell. You can unmute and tell me the answer. Class யாருமே கவனிக்கிறது இல்ல.
Ma'am,
Yes.
ma'am, either can we call two delays
Yes.
or else we can try approximating 3 times of single delay.
Okay.
Because first delay is 3
Actually,
milliseconds.
we cannot approximately call 3 times of delay here. Okay. You can call single delay with different initial values. Okay. So that is the exact logic of this program. So first you have to calculate initial value of the timer for on time. Okay. So on time 65536 minus 10 millisecond on time is 3 millisecond. Okay, 3 millisecond divided by 1.085 microsecond. What is the answer for 3 millisecond?
62771, I think so. Approximately.
Hexadecimal value?
F533 approximately.
F8?
F533, ma'am.
F533. Okay. And next, for 10 millisecond off time?
DBFF, ma'am.
dB?
FF.
FF.
Yes, ma'am.
Okay. So the logic here is, first you have to identify your T mod value. Find out the T mod value. So what is the T mod? Move hash 01 in case of 60-bit timer. Next, load your initial value for on time. Okay. So load your initial value. Next, move FF for your on time and call delay. Okay. Again, move TH0 with your initial value of time, move TL0 hash P naught comma hash 0 and call delay. And SJMP L1 comes here, okay. And next, in case of delay, same procedure. You start the timer, monitor your overflow flag. Once overflow is set to 1, clear T or not, clear overflow flag. So first load your on time initial value and FF2 P naught for generating high pulse, okay. And next you load your off time initial value and move 0 to P naught and call the delay routine. In delay routine you have to incorporate your timer instruction. That's all, okay. So what is the next one? Next problem. Write an ALP to generate rectangular waveform of 50 Hertz of 25% of duty cycle on P1.0. So what is the logic for this program? Yes. Yes,
Ma'am, for the previous program,
okay.
and can we set a carry for on time?
Okay.
And we will check a jump no carry instruction in the delay, ma'am. If there is no carry, then the corresponding mod value,
What is the purpose of carry?
To change between the on time and off time within a single delay.
Okay.
Initial
So
values will be changed.
what is your logic? Please tell me.
Before calling the delay function, we can set a carry, ma'am, for
Okay.
on time purpose.
Okay.
And for off time purpose, we will clear the carry. In the delay function, we will call a jump no carry and corresponding initial values will be placed. Before jump no carry, the initial values of on
I
time will
can't understand. நீங்க the code போடுங்க. I will go through that. Okay. So regarding this, your rectangular waveform generation, first you calculate the time period for 5 Hertz frequency. What is the time period? Students, post your answer. Convert your frequency into time period for 5 Hertz. What is the answer? 0.2 second. Okay, so 200 millisecond. 200 millisecond. So 20% duty cycle. So in 200 millisecond, we have to calculate the value for 25 duty cycle on time. Okay, for 200 millisecond, 25% value for 200. What is the 25% value? 50. So 50 will be your 50 millisecond will be your on time period, and 150 millisecond will be your on off time period. Okay. So here in this problem, so 1 divided by 5, so 200 millisecond. So this can be divided into 50 millisecond plus 150 millisecond for 25% duty cycle. So first calculate for 50 millisecond. So 50 millisecond divided by 1.085 microsecond. So find out the value. And subtract this value from 65536 and convert that value into hex. Please tell me the hex value. 50 millisecond divided by 1.085 microsecond. Okay. And subtract that value from 65536 and convert that answer into hexadecimal. What is the answer? Four six zero eight two. Subtract that value from 65536 and find out the hexadecimal value. (4BFE). All of you getting this answer? 4BFE. Students, please respond. All of you getting? So 4BFE is correct or not? So the logic is so first set bit P1.0 for generating your on time, and next call delay routine. Next clear. So this is for 25% duty cycle. And for off time, we have to call delay 3 times. A call delay, A call delay, HJMP, L1. So this is for 75%. So in delay routine, so similar to your previous program, initialize your T mod. So T mod value is 0, 1. And initialize your higher order register and lower order register based on your timer calculation, and start your timer. Monitor your overflow flag. Clear the run control bit. Clear the overflow flag. And this subroutine should be terminated with return instruction. So this will generate 25%. When we are calling this delay for 3 times, will generate 75% of duty cycle. So that is the logic. Please note it down. So any doubts? Set carry, again clear carry. P naught is loaded with, okay. So first, actually initial stage, first FF is loaded into P naught. Okay. So you are going to set the carry flag. So what is the condition to be checked here after this set carry?
Ma'am, the condition will be checked in the delay function, ma'am. Based on the carry, the initial values will be loaded.
Okay, set carry kapra you are calling delay. Delay la vandu you are going to check the carry flag status. Okay. So appa vandu carry vandu is not set அப்படினா program control transfer here. Okay. It's correct one. And this SJMP goes to L0. Where is L0?
Ma'am, set the timer. Set
Oh.
BTR.
Okay, ma'am. So any doubts regarding your timer operation? So next we will move on to counter operation. So timers can also be used as timers, counters, counting events happening outside the 8051. Okay. So when it is used as a counter, it is a pulse outside of the 8051. So based on the pulse, your timer start counting, and based on that, your TH, based on that clock pulse, the content of TH and TL will be incremented. So mainly two pins involved for applying external clock pulse. One is port 3.4 and other one is P3.5. So this P3.4 is for timer 0 operation and P3.5 is for timer 1 operation. So Tmod and TL that is all your Tmod register and TH and TL register are the same for the as for the timer discussed previously. Okay. Same registers can be used for counter operation, but the only difference is we have to send the external pulses through P3.4 and P3.5. Okay. And other important thing, in Tmod register, this bit should be 1 in order to activate your counter operation. The C bar T must be 1 to activate your counter operation. So two pins mainly involved, that is pin number 14 and pin number 15. So pin number 14 is P3.4, 15 is P3.5. So the function configured is for 3.4 timer 0 and this one is timer 1. So P3.4 is for timer or counter 0 external input and this is for timer or counter 1 external input. The important thing, the C bar T must be 1 to activate your counter operation of timer. Okay. So this is the internal block diagram of your counter. So only the basic difference between your timer and counter block diagram is that here. So the source of clock pulses are from P3.4 and 3.5. So based on the clock pulse, it will perform increment operation, and based on the clock pulse, the count will be incremented in TL1 and TH1. Okay. So remaining operations are very similar to your timer operation. So this switch is for timer or counter operation and this is for hardware and software way of starting the timer. So only difference, it will get the clock pulses from the external inputs. The external inputs are P3.4 and 3.5. That's all. Please note down this problem. Assuming that the clock pulses are fed into pin T1. So T1 is nothing but your 3.5. So I am applying external clock pulses to P3.5. So write a program for counter 1 in mode 2 to count the pulses and display the state of TL1 count on P2. Let's assume 8 LEDs are connected to P2. So timer 1 as an even counter fit into P3.5 So we have to configure this P3.5 as input pin while programming this application. Okay. So write a code for this particular application. So first step, you have to find out T mod value based on this mode selection. So first you find out T mod and tell me the answer. So here counter 1, mode 2 will be selected. So what is the T mod value? Zero one. Raghavendra, correct. So the answer is 60 in binary. So first move your T mod value. Hash 60. That is 0, 1, 1, 0, 0, 0, 0. So this is for C bar T, 1, 0 is for mode 2 selection. And timer 0, all the bits are 0. Remaining all the bits are 0. So next we have to clear our TH1. Because since it is in 8-bit auto reload, you have to clear this higher order register. Okay. And next, for applying external clock pulse, I am using P3.5. So first we have to configure this P3.5 as a input port pin. So for that I have to use this instruction. So make T1 as input, your timer 1 as input. Okay. So once it is done, next you have to start the timer for start counting the external clock pulses. So start the timer and get the copy of your TL because it will perform increment operation. So based on the clock pulse, the TL1 count will be incremented. On receiving each clock pulse, the count will be incremented. So move that is TL1 value to accumulator. Because for getting every clock pulse, we have to change the status of P2 based on your problem statement. So we have to display the status of TL1 count on P2. So move your accumulator value on P2. Okay. So every time get the count from TL1 and move that value to P2 and monitor your overflow flag. So your L1 should come here. So continuously this loop will get executed till F1 is equal to 1. Okay. So after that you clear TR1 and clear TF1 and SJMP L2 should come here. Start your timer. So the operation is completely different from your timer operation. In case of timer, we are loading some initial value into your timer higher order and lower order register. Once timer gets started, your timer module will incrementing the value starting from your initial value of the timer to the maximum value of the timer. After that, when the maximum value is reached, the overflow flag will be monitored. But here we have to clear your timer register and start your timer. On receiving each clock pulse, you have to move the lower register content to your P2. Since 8 LEDs are connected to P2, this will reflect the status of your TL1, and after that monitor the overflow flag. One overflow flag is set, clear the timer, that is stop the timer and clear the overflow flag. Is that clear? Is that clear? Okay. So let's run this code in KEIl Microvision. So what are the ports involved in this particular application? Port 2 and your P3.5. 0, 1, 2, 3, 4, 5. Okay. So let's run this code. Here you can see your counter mode is selected. Okay, and your counter is in 8-bit auto reload, and T mod value is 60. So 60 is loaded into T mod, and TL1 is initially cleared. Okay, so I am going to change this particular 3.5. Okay, so the count will be 1 now. So the TL1 holds 0, 1. Next, I am clicking this 2. Next, I am clicking this 3. So this is the difference. In case of your timer operation, timer will get started means it automatically counts the clock pulses. Here, based on the input, the counter register content will be incremented. So that is the difference. So in this Proteus, so here I have connected this pulse generator to 3.5. Okay, let's simulate this code. See, you can see it's continuously counting the clock pulses, and the same value will be reflected in the P2. So you have to connect LED, 8 LEDs in order to view your outputs, and you can see the values are continuously changing. Instead of clock pulse generator, directly you can give manual inputs by using this logic gate. Okay, suppose I am giving 1 clock pulse, so the count will be incremented. 2. Here you can see the last 2 bits are turned on. Okay, so based on the input, the count will be incremented. So can you understand the difference between timer and counter? Can you understand? Can you understand the difference between your timer and counter? In counter case, you externally you have to apply some clock pulses to pin 3.4 and 3.3. Okay. So that's all about your timer. So timer counter programming is completed here. So any doubts regarding your timer operation and counter operation? Just I will give some introduction about interrupts. So next topic is 8051 interrupts. So interrupt is nothing but it's a external or internal event that interrupts the microcontroller to inform it that a device needs its service. Okay. Suppose your external device requires attention of your microcontroller, it can interrupt the microcontroller directly through your interrupt signal. So that is the definition of interrupt. Okay. So first we need to understand what are interrupts and what is the difference between interrupt and polling. Okay. So first I will explain polling. So consider three devices, device A, device B and device C. So consider three devices, device A, B, C. So these devices may request some service from microcontroller. So let's assume these are interfaced with your microcontroller, 8051. Okay. So these devices may request some service from microcontroller at any time or may provide some information to be processed. Okay. So your microcontroller can handle these three devices in two different ways. One is polling, other one is the interrupt. Okay. So in the polling method, so what microcontroller will do is, first microcontroller will check each device for any pending request. So every time it will check the device individually for any pending request. First it will check device A for service. Okay. If the request is found, it will service it. Next it will check for device B and next it will check for device C. Okay. So microcontroller keep repeating sequence of checking these devices to all the time. Okay. So what is the drawback involved in this method? So every time it will check the device request and service the request, and next it will check for the next device, service the request. So it will keep repeating the sequence of checking these devices all the time. So what is the drawback of polling method? So what is the drawback? So for example, your timer operation. In timer operation, so what we are doing actually in case of generating square wave, we are continuously, that is our program was monitoring your overflow flag all the time. So what is the drawback in that method? That is the example of polling. So every time your microcontroller will check the status of your overflow flag status in case of your square wave generation. What is the drawback in polling method? So the drawback, we can see the drawback of polling method. So microcontroller will waste a lot of time for monitoring devices, that is for any available data or service requests. Okay. So that is the drawback of polling method. So that can be solved by your interrupt servicing mechanism. So there are two ways. One is the interrupt, other one is the polling. The drawback of polling is the microcontroller will waste a lot of time monitoring devices for any available data or service request. Okay. So either way, some of these devices is to use interrupt whenever some device have data available for processing or have service request. For that case, it can send interrupt signal to the microcontroller. Okay. So at the reception of interrupt signal, microcontroller will stop all its activity and handle the same request. Okay. So it need not check the status of every device. When the signal is generated from the external device, it will directly interrupt the microcontroller. So at that time, your microcontroller will stop all the activity and handle the interrupt. Okay. So that interrupt signal may be sent from either external or internal. So that program is associated for executing the interrupt request, the program which is associated with the interrupt is called interrupt service routine or interrupt handler. So comparing these two methods, interrupts are far better than polling. That is because the use of interrupts, the microcontroller can handle multiple tasks easily and efficiently. So the function or program is responsible to handle these interrupt requests is called ISR. So next class we will see about remaining things. 8051 interrupt organization and steps in executing our interrupts and special function registers of 8051 interrupts. Okay. Any doubts? Okay. Okay. Thank you. Thank you.